Following Einstein's theory of general relativity, Alexander Friedman was the first scientist to mathematically predict the notion of an expanding universe via two equations, which he derived directly from Einstein's equation of general relativity. The fundamental assumption to the Friedman equations is that regarding the cosmological principle, this states that our universe is spatially homogeneous, universal, and isotropic, meaning that, on large scales, part of the universe, also known as the local universe, has the same physical properties throughout, looks the same regardless of direction to an observer, and abides by all the physical laws everywhere.
So now we know the basic idea behind the Friedman equations, but what does each component within it mean? Well, as mentioned before, we know that these two equations are different ways of writing the same formula with different values in them. So we see that the first one is related by rho, time, and k, and the second one differs in that it is related by rho, p, and the speed of light. But what do all of these letters mean? Well, A represents a dimensionless cosmic scale factor as a function of time. It indicates the relative expansion of the universe and effectively relates the proper distance between a pair of objects undergoing an isotropic and homogeneous expansion. It can also be related to the redshift through this equation. Rho is the density of the space in question. This includes of all matter, radiation, and a cosmological constant within the space. K refers to the curvature of the space and can also be related to the pressure P. G is Newton's gravitational constant, and lambda is the cosmological constant. This originates from the idea that a vacuum is not perfectly empty. Instead, it has particles and their antiparticles constantly annihilating each other. So in theory, a perfect vacuum has an energy density similar to the cosmological constant. So now we know what each component means.
Well, that's a very good question. K, as mentioned, is the curvature, and this can be used to indicate the shape of our universe, whether it is spherical, hyperbolic, or flat. And this is determined by taking the ratio of the density over the critical density. The critical density itself is calculated by dividing the curvature by the radius of the amount of space that we're considering, and this result is used to determine omega. Omega determines the curvature and so the shape of our universe, as well as, of course, the behavior of light traveling through the universe. This is important because it allows us to understand deeper how physical laws apply to our surroundings. There are three different possible outcomes. If the density is more than the critical density and omega is greater than 1, the universe would be spherical and parallel light beams would converge. If the density, however, is smaller than the critical density, omega being smaller than 1, the universe would be hyperbolic, meaning that parallel light beams would diverge. However, from observation and experiments, we can see that the case for our universe is that parallel light beams remain parallel, showing that the critical density is equal to the density, giving omega equals to 1. Therefore, our universe is cosmologically flat. Another application, which is arguably the most important for Friedman's equations, is Hubble's constant. Hubble's constant can be determined by integrating Friedman's equations a couple of times with respect to the constant itself, and when substituted into Hubble's law, given a specific distance, we are able to determine the rate of the expansion of the universe, as well as its age.